Hello everyone again. This is lecture 3 part 2 of current electricity. We will go on with the further discussions of example 3.2 only. So let's start the discussion only directly. I am Sameer Lavankar. Let's begin our discussion. So right now we are on the fifth concept, that is drift of electrons and the origin of resistivity. Let's look over this discussion only here. So A and B parts were being explained in the previous lecture. Let's move on with the C part. So what does that C part say? That if the electron drift speed is so small as the electron drift speed is, which we got in the previous example, was 1.1 mm per second, and the electron's charge is small, electron's charge is also small, that is 1.6 into 10 to the power minus 19 coulombs. So it is 1.6 into 10 to the power minus 19 coulombs here. How can we still obtain large amounts of current in a conductor? Sometimes the current is of the order of 10 to the power, let us say 6 to 10 to the power 8 amperes also. So how can we obtain such large amounts of currents even if the values of, you can say, electron charge also and the drift speed is very small? So let us look to the solution of this also. So because the electron number density is enormous, as the electron density is enormous, that is 10 to the 29 per meter cube. So let us, what does it try to say is, if I have 1 meter by 1 meter by 1 meter amount of sample, let us suppose I have this as the sample, even if I this is, let us say 1 and 1 here, then the amount of charges, the amount of charge, that is a capital N value if I am not wrong, is equal to 10 to the power 29. Even if I multiply this by 1.6 to 10 to the power minus 90 to take out the value of charges here also, then it is nothing but 1.6 into 10 to the power 29 minus 19 gives you 10, I guess. So 29 minus 90 gives you 10. So amount of charge is in the powers of 10. So if these are in the powers of 10, then the amount of electron amperes current which can produce can also be enormous. It can be, even if it is even if in the power 10 to the power 10 also, then I think it is very crucial, it is very easy to make amperes of the order of 10 to the power 6 or 10 to the power 8 amperes. So because so the answer for this is because the electron density is very high, hence the value of charges current such as 10 to the power 6 or 10 to the power 8 can be obtained. Okay. So this thing is also being done. Next point is, when the electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? So by no means the drift velocity is superposed over the large random velocity of electrons. So it does not happen in this case. So it is just a simple explanation that why does not happen, another potential cannot happen, lower to higher potential. So these are just simple method, only the A and B part were of enormous nature because these are involved with drift velocities only. So please look over the last point here. So are the paths of electrons straight lines between consecutive successive collisions in the absence of electric field and the presence of electric field? So what are the paths of electron field distribution? So in the absence of electric field, the paths are straight lines, quite evident, because let us suppose if I try to make some electric field here. First of all, because there is no electric field acting, there will be no external force which is put upon on these electrons. Hence there will be a straight line motion if the collision is being happening. But because of an electric field present, let us suppose this is the electric field which is present, there will be an external force happening, there will be external force which will pass on the electrons due to, let us say, positive charge or negative charge, such as repulsion or collision, repulsion or attraction, and hence there will be a deflection, occurring on these electrons directly because of electric field. So this is being only explained, and hence we can say that for no electric field, in the absence of electric field, the complete movement or paths are straight lines, but in the presence of electric field, these paths can be in the curved lines. So I can just explain, just iterate the line here. So in the absence of the electric field, the paths are straight lines, but in the presence of electric field, the paths are in general curved. So this is the only explanation being explained here. Okay. So that is the end of second example here. Let us move on to one of the crucial concept of this concept only, that is mobility. So after this mobility concept, we can directly go to limitations of Ohm's law. So please look over here. What is mobility? So as we have seen, conductivity arises from mobile charge carriers, quite evident, everything. So mobile is basically a movement, anything which can move from point A to point B are nothing but called as mobile. So as they are as the conductivity, what is conductivity? Conductivity is basically, we can assume it to be inverse of resistivity, and resistivity is nothing but the resistance which the conductor offers for the movement of electrons from point A to point B. If the resistance is higher, that means it takes a large amount of energy for the passage of current from point A to point B, or the passage of electrons from point A to point B. Okay. So as we have seen, that conductivity arises from mobile charge carriers, quite evident. in metals these mobile charge carriers are electrons. As we know that we have assumed, initial assumption is that only that the movement of electrons will only constitute an electric current and the ions will be fixed ions, fixed positive charge will be there, and the negative electrons are only capable for the movement of or the constitution of electric current. Okay. So, in metals these mobile charge carriers are electrons. In an ionized gas they are electrons and positively charged ions. In an electrolyte these can be both positive and negative ions. So, just a theory part for you again. So, till our current electricity concept is going on, we are only assuming that electrons are moving, but you should also remember that in an ionized gas as in any gas, the gas present in let us say ionosphere is an ionized gas. Why it is called as ionized gas? Because it also constitutes positive and negative ions. So, in an ionized gas there are electrons and positively charged ions, and therefore also in an electrolyte. What is an electrolyte? Electrolyte is just a solution. Electrolyte is nothing but a chemical solution which are having both positively charged particles also and negatively charged particles also. This is nothing but a electrolyte. So, an electrolyte, these can be both positively and negative ions. So, this is the only explanation explained here. Let us move with the further discussions. So, this is just a theory part. Now, an important quantity that is called as mobility is defined as the magnitude of the drift velocity per unit electric field. So, you just need to remember it is just another concept, just another denotation. So, nothing but, as we also denoted something called as J, which is nothing but the current per unit meter square. So, therefore, there is another concept which is called as mu. Mu is nothing but the mod of Vd. Please remember it is mod of Vd upon the electric field. So, please remember another concept which is called as mobility. If there is an application of mobility, I will try to explain you in the subsequent slide, but for now just remember that mobility, which is defined as mu, is equal to mod of Vd upon capital E. And you know value of mod Vd. So, let me just write it again. Mod Vd is nothing but small e capital E by m into tau, where small e is the charge of an electron, capital E is the electric field, small m is the mass of electron, and tau is the relaxation time. Okay, so if I just divide, it by E also, it gives you the value of mobility, which is equal to small e by m up into time. So, let us move on. So, the SI unit of mobility is meter square plus per voltage second, and is 10 to the power 4 of the mobility in practical units. That is, in practical units, if we need to see the number very clearly or in a number pattern which we can directly utter. So, in mobility in actual patterns we always use the term centimeter square per voltage second, but the SI unit, as we know, the SI unit is always for the length, it is always captured in meters, hence we should write the SI unit as meter square plus upon voltage second, but in practical units it is always centimeter square per voltage second. Okay. So, this thing is also being explained, Mobility is positive, quite evident, as the value of mod of Vd is always positive and E is always positive, hence mobility is always positive. Okay. Next is, from the above equation of Vd, we have mod of Vd is equal to small e by m into tau. This is the same expression which is explained here also. Hence, just mu is equal to mod of Vd by E, which is equal to E tau by m. So, this is a similar expression which I also derived here. So, it is nothing but just calculation of deduction of capital E value, where tau is the average collision time for electrons, which we have also explained in the concept when we are trying to origin resistivity, when we understood the concept of origin of resistivity. There also we found that tau is nothing but called as relaxation time, which is also called as summation Ti by n. What is Ti? Ti is the amount of time required for the successive collisions to occur, or of collision of a one electron 1 to let us say electron 2 to occur, and therefore, the average of electrons per unit capital number of electrons is equal to relaxation time, which is denoted by tau. So, this thing is also been explained. So, this was the complete end of your drift of electrons concept also. Let us move on to the next concept now, which is called as limitations of Ohm's law. So, quite evident that from the picture only that the V is equal to IR concept is not valid in every sequence, it is not valid for every sequence, it may utter. So, let us suppose if I make a diagram of this to be V, this to be I, then it is not, if the Ohm's law is satisfied, then the velocity or the resistance should always be a constant slope of capital R, but it try to deviate, let us say deviate in this direction, or let us say try to deviate in opposite direction, or it is not the same. If I change the value of voltage and current, what happens, what are the significances, what are the different ways in which the limitations of Ohm's law have been occurred, we will try to explain in this concept here. Okay. So, although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. What does the meaning of this is that V is always not proportional to I in those situations. In these situations, V is always not proportional to I. If I write it here only, so V is not always proportional to I. Okay. So, the deviations broadly are of one or more of the following types. So, the first deviation is that V ceases to be proportional to I. So, this thing can be explained as this form, that till one point, till some point, let us say if I denote it by this portion somewhat here. So, till this point the Ohm's law was valid, but after this, as you can see that if it would have been current, then the resistance would have gone, the velocity or initial current direction would have gone here, but it tries to deviate from this portion here. That means the value of resistance keeps on changing. Okay. Second is the relation between V and I depends on the sign of V. In other words, if I is the current for a certain V, then reversing direction of V keeping its magnitude fixed does not produce a current in the same magnitude as I in the opposite direction. This happens for example in a diode. So, let me try to explain you what does the point B tells you here. So, what the B tells you here that there should be an explanation. Let us suppose if I make a closed circuit, let us suppose this be the resistor. Let us suppose this to be the battery, and let us say this is the positive and negative charge here. Now, what does it try to say is that let's say the voltage of this is already being known. The voltage of this is already being known. Here, due to the positive and negative direction here, there should be a movement of current in, let us say if I am if I am taking a direction from positive to negative direction here in the direction of this. So, let us say this is the current direction here, and some current I is produced. Now, if I try to explain, or if I try to change the polarity of the battery, let us suppose I change the polarity, let us suppose I put the minus sign here. So, let us say I change the polarity. So, this time the current direction will be like this, but even if the current direction is like this, if the concept of Ohm's law, that is V is equal to I should be valid in every case, but when it was tried to elaborate or make a graph for this situation, the graph came out to be like this. The example of this graph is called as a diode. Diode concept, you will get to know about diode concept in the chapter of semiconductor devices, but for now just listen to this concept only, that there is something called as diode. Diode is a device. If I try to reverse the current in the diode, then the amount of resistance which it offers has a non-linear. First of all, it has a non-linear sense, and even if it has a non-linear sense, in the opposite direction, as you can see, the graphs are not same. This graph is not equal to this graph. Hence, this is also a deviation from the Ohm's law, and hence it is a limitation. So, this thing is also been explained. Let us move on to the next slide now. So, the C portion says that the relation between V and I is not unique. That is, there is more than one value of capital V for the same current I. So, as you can see in this diagram here, there are instances, there are some materials in which for the constant value of V there is different values of I. As you can see for this portion, if I try to make a portion from this here, there are two voltages. There are two voltages which have the same value of velocity, that has the same value of current I. This is not the case in every sequence, because if the Ohm's law is valid, the resistance just keeps on increasing. There is no deviation from either sense. If I take the velocity voltage here and the current here, so if this is happening, then this is also a deviation from the limitation, deviation from the Ohm's law, and hence this is also not the case. Hence, the relation between V and I is not unique. That is, there is more than one value of capital V for the same current I, as I already explained to you. A material exhibiting such behavior is GaAs. GaAs is also called as gallium arsenide. So, gallium arsenide is a substance which is responsible, or which is an example of this concept here. So, in easier form we say it as GaAs or gas. So, materials and devices not obeying Ohm's law are widely used in electronic circuits. So, because such that to increase the efficiency of the electric circuits or to decrease the leakage of current, sometimes these all things are being used. The only and only purpose to use this is to increase the efficiency, or to increase the power, or to transmit the current power from point A to point B very efficiently. These all things are used. Okay, so that is the end of, I think, Ohm's limitations of Ohm's law. Let us move on to next concept now, that is called as resistivity of various materials. So, what is resistivity? We have already explained to you, just iterating it again here. So, according to Ohm's law, we know that capital V is directly proportional to I. This is only and only valid till the Ohm's law is valid. So, we are assuming that the Ohm's law is valid. Ohm's law is valid. Okay. Now, if Ohm's law is valid, we can remove the proportionality sign and include it by using the value of Q equal to, and hence V is equal to IR. V is equal to IR, where R is nothing but called as resistance. Okay. Now, the resistance concept is being dealt with. It was found that the resistance value depends upon the dimensions of the conductor. Hence, when it was found out, it was found that the resistance is directly proportional to L and inversely proportional to A. Now, if we remove the proportionality sign here also, we got a new concept or new denotation which is equal to rho here, rho L by A. Now, this thing is called as resistivity. So, now let us try to learn more about this concept called as resistivity in this lecture here. So, resistivity of various materials. So, the resistivities of various common materials are listed in the table. So, this is the table being explained here. So, this is that table in which the resistivity of different materials are being explained. As you can see, some are conductors, some are semiconductors, and some are insulators. As we already know, which are the best which are the things which have most affinity for electrons or most value of free electrons so that the collisions could occur are conductors. Then it is followed by semiconductors, and the least are by the some devices or substances called as insulators. Okay. So, the materials are classified as conductors, semiconductors and insulators depending on the resistivities in an increasing order of their values, quite evident. So, the maximum value will be for a insulator, and the minimum value of resistivity would be for a what we can say this in conductors. Okay. As you can see, the powers also vary. So, here for conductors the value is of the order of 10 to the power minus 8, and here the value of 10 to the power 16. So, as you can see, the order of magnitude increase in a very larger sequence till we go to the end point of these insulators. So, the metals have low resistivity in the order of range of 10 to the power minus 8 rho meter to 10 to the power minus 6 rho meter, quite evident. So, this thing is also been explained. As you can see, why the value of ohm meter is being came into sequence. So, let us suppose this has been denoted by ohm here. If I just send A by L here, then it is meter square by meter. Meter gets cancelled. Hence, the unit which we got for resistivity is nothing but ohm meter. So, that is why ohm meter came into sequence here. Okay. Next thing is at the other end are insulators like ceramic, rubber and plastics having resistivities of 10 to the power 18 times greater than metals or more. Quite evident, as you can see that these are of the order of 10 to the power 10 to the power 14, 16 and these are the orders of them. Okay. Next is in between the two are semiconductors, quite evident. So, those are the values which are why are there a concept called as semiconductors will be dealt in a concept dealt in a chapter which is called as semiconductor devices. So, why there should be a substance called as semiconductors, what are the influences, what are the effects of the semiconductors will be explained in that chapter only. The semiconductors are very useful devices for our electrical engineering concepts. Okay. These however have resistivities characteristically decreasing with a rise in temperature. So, resistivities are inversely proportional to temperature, this thing is explained here. So, resistivity is inversely proportional to temperature. The resistivity of semiconductors are also affected by the presence of small amount of impurities. This impurity concept is very important for our electrical engineering. You will be dealt with this in the concept of semiconductor devices only. Okay. Next is this large feature is exploited in the use of semiconductor for electronic devices. So, this thing is I already explained to you. So, let me stop it here only. I will try to explain you from this lecture from this point only in the next class. I will try to look over this again and then we will move on with the further discussions of resistivity of various materials. So, let me stop it here only. Thank you.